Everyone asks, what's the range? Almost nobody asks, what's the chemistry? But the chemistry is the part that secretly decides how your EV feels, charges, ages, and even how safe it is. In this video, I want to show you why two cars with the same battery size on paper can feel completely different in real life, just because the atoms inside the cells are arranged a little bit different. And once you see that, you'll never look at 60 kilowatt hour or 400 kilometers range the same way again. Let's start very simple. Think of battery chemistry like the personality of the pack. LFP, NMC, NCA, sodium, whatever, those aren't just nerdy labels. They're like saying this person is chill and slow, this one is fast and moody. Same job, store energy, but totally different moods. Take LFP first. Lithium iron phosphate. This is the calm one. It doesn't store as much energy per kilogram, so for the same range, the pack is usually heavier, but it's stable, it doesn't freak out at high temperatures as much, and it can handle a lot of cycles. That's why you see it in cheaper EVs, buses, and cars where the brands say, we want this thing to last forever and not to catch news on fire. It's like a big, strong marathon runner, not a sprinter. Now compare that to NMC or NCA chemistry, the nickel-rich chemistries. These are the athletes that live on the edge. More energy in the same space, more power, great for long-range cars and high-performance models. But the trade is, they are peakier. They need more careful cooling, they can age faster if you hammer them with fast charging, and use more expensive metals, like nickel and cobalt. Amazing range and power, but they want you to respect their limits. And that's the first big point. The same 75 kilowatt hour pack in the LFP versus NMC might feel totally different. The NMC car might be lighter and punchier. The LFP car might be heavier and cheaper and more chill about daily charging. Here's the problem most buyers don't realize. We talk about range as if it is the only number that matters. But chemistry is what sets how hard you can floor it before the pack heats up, how fast you can charge before the BMS slams on the brakes, how quickly the battery loses capacity over years, and how safe the pack stays when something goes wrong. Imagine two EVs sitting at a DC fast charger in winter. One has an LFP pack, one has a nickel-based pack. On the spec sheet, they both say 10 to 80% in 20 to 30 minutes. In the real world, the LFP pack might hate the cold more and refuse to take full power until it's warmed up. You plug in and the car babysits the pack for the first 10 minutes, while the heater works. Same station, same cable, different chemistry, different mood. Or think about repeated launches, hard driving, and towing. A chemistry with lower internal resistance can push more current without turning into a space heater. That means less voltage sag, more stable power, and less stress on cooling system. If you ever felt your EV pull strong at first and then slowly soften when pack gets hot, that's your chemistry and thermal system showing their limits. Now let's go deeper than just LFP versus NMC. Inside each chemistry, there are trade-offs between power and energy. Some cells are turned to be energy cells. They pack in more capacity but can't handle huge currents. Others are power cells. They can dump or take a lot of amps, don't hold as many watt hours per kilogram. Others are power cells. They can dump or take a lot of amps, but don't hold as many watt hours per kilogram. A performance EV might use cells that lean toward power, so it can do repeated launches and hard regenerative without crying. Here's where the challenge gets interesting for engineers. You don't just pick a chemistry, you pick a chemistry that matches the story of the car. If you design a small city EV with LFP, you get something like cheap, durable, very safe, perfect for daily commutes. But maybe a bit heavier. If you design a sporty highway monster with NCA, you get crazy range and acceleration, but now the BMS and cooling system have to work hard to protect it from fast charging abuse and hot climates. So when you see brands make different choices like Tesla using LFP in some base models and nickel chemistries in long-range ones, that's not random. It's chemistry matching the job. Let's talk about degradation, because this is where chemistry really shows its teeth. LFP tends to age slowly if you don't torture it with constant full charges in high heat. It's more comfortable sitting at higher state of charge than nickel-rich cells. Nickel chemistries tend to hate setting at 100% while hot. Leave them there, and they will quietly lose capacity faster over time. That's why you hear so many recommendations like charge to 80% daily on certain cars. Now imagine two owners. Owner A has an LFP car and happily charges to 100% every night in a cool garage. Owner B has a nickel-based pack, parks outside in the sun, and also charges to 100% every night. After several years, owner B is more likely to complain that their range took a hit. Same habit, different chemistry, different results. And behind all of this, the BMS or battery management system is trying to compensate. It knows the chemistry, it knows the voltage curve, the resistance growth, the safe temperature window. It sets charge limits, power limits, and regenerative braking limits based on what that chemistry can handle today, not what the brochure says. So when you feel your car reduces fast charging power as it gets older, or you notice regenerative braking is weaker when the pack is cold, that's not just a random software, it's chemistry aware control. Battery chemistry is not just a spec in a PDF, it's the script your BMS follows every second the car is on. It decides how honest your state of charge gauge is. It decides how your range drops in winter. It decides the shape of your charging curve, and etc. Two cars with 70 kilowatt hour usable battery pack can give you very different driving experiences simply because one is LFP with a flat voltage curve and the other is NMC with a steeper one. So next time you compare EVs, don't stop at range and price. Ask what chemistry does it use? How does that chemistry behave in cold? How does it age at high state of charge? Is the brand known for conservative BMS limits or aggressive ones? Those answers tell you whether your car will feel strong and consistent at 150,000 kilometers or tired and gumpy. To wrap this up, range is just a headline. Chemistry is the story. If you understand the chemistry, you understand why your EV behaves the way it does today and how it's going to behave 5 or 10 years from now. And if you want to go deeper into how the BMS actually uses that chemistry data to control charging, power, degradation, hit the BMS course link in the description. Thank you.